I'd like to start out with this that I don't represent my employer. The deal is I get to do presentations and I don't represent them, so that's how it works. There's another Tony Stieber who also does information technology presentations. So although I will answer by Tony, I usually go by Tony. For purposes of identification, I go by Anthony J. Stieber. And I've got an email address there that you can use to contact me. Now this presentation is about how not to implement cryptography through the OWASP Top 10. So I'll be bringing up failed examples, some use cases, but everything that I'm going to be talking about are real-world examples that I've seen out in the real world, and they're published examples. So there's no proprietary information, no insider information here. This is what's available out there, but I can confirm there's more to it than just this. But I can't say more than that. I'm not a real programmer. As I was introduced, applied cryptographer is a good term for what I do. But I do have a background in coding and programming. The example here, if you're familiar with the editor wars, I actually predate Vim. My first Unix editor was Emacs, GNU Emacs, closely followed by VI, and then back to Emacs, VI. I have used Ed. I do occasionally use Cat, and today I use Vim. But since then, I've moved on to more sophisticated software. Oh, and I'm not even a programmer on TV. I do use actually Notepad quite a bit, and I even use it for this presentation, because I just don't do much coding anymore. So before I get into some real deep detail, I'm not quite sure exactly what people are looking for here. So are anyone here who's a complete beginner to information security? Okay. Then I won't explain exactly what the ACI Triad is. I prefer ACI versus CIA Triad. It's less ambiguous. It's also in alphabetical order. And when it comes to cryptography, there's not a whole lot that can be done in availability. There's a little bit, but it's not very common. But for confidentiality, yeah, there's ciphers, for example. But there's also, for integrity checks, that can be done cryptographically, and that's an important part of cryptography that's often misunderstood or just unknown. There is an exception for availability. There's what's called the Blakely-Shamir secret sharing schemes. There are a class of algorithms, and they can work very well for availability, but they're very rarely used actually in the real world. They are out there, and there are commercial products that support it, and there's even an open source implementation called SSSS, the Shamir secret sharing scheme software. But I have not actually seen anyone actually use it, but I know it's out there. There are some terms I'm going to use. Is anyone here completely new to cryptography in general? So there are terms that I might need to explain a little bit more, acronyms, abbreviations. Okay. So I'll just very briefly state this. Cryptography is about making and keeping secrets. Cryptanalysis, that's the flip side of cryptography, that's breaking the secrets. And that's really important too, because if you don't know how to break them, then if you don't know how to break them, people who try to make them are not going to be very good at it, because they aren't good enough to know how to break them, so they're going to make things that are weak, strong. So usually the best place to start is in cryptanalysis and then move to cryptography. But in the commercial world, very few people start out doing cryptanalysis. There's not a whole lot of business doing that. Not in the open anyway. That's primarily government, military that do the cryptanalysis, so they're really good at it. But in the commercial sector, not so much. So there tends to be a lot of really bad cryptography out there, and it doesn't take a lot of cryptanalysis to break it, unfortunately. Cryptology is the wider field that incorporates cryptography and cryptanalysis. I'm also going to use the term just crypto, where I could mean really any of these. And if I need to be more specific, I will, but I'll use crypto as an abbreviation for that, for this field in general and cryptography in particular. A really important idea is Kirchhoff's principle. Kirchhoff's principle is very important in cryptography. It's pretty much a cryptographic concept. And it means to build systems and make an assumption, something that's called Kirchhoff's assumption, that you should depend solely upon the secrecy of the key, the cryptographic key that's protecting your data. If you don't assume that, and you assume you can keep other things secret as well, like your algorithms, your protocols, that makes your system more fragile, and it tends to make the system insecure overall. The more things that you have to keep secret, the less likely you're going to be able to keep them secret. So Kirchhoff's principle is a really good assumption to make in when building and designing crypto systems and implementing them. I'll skip over these for the most part, but there's algorithm. Algorithm I'm going to use in the cryptographic sense, but there's nothing special about cryptographic algorithms other than cryptographic. They're still, it's computer science, it's mathematics. A cipher is a very particular kind of algorithm. And then there are hash functions, which are also another kind of very specific cryptographic algorithm. And then random number generators, which technically speaking aren't algorithms at all. If there's an algorithm involved, you're actually making a mistake. And then in addition, ciphers encrypt plain text into ciphertext, and then decrypt ciphertext into plain text. So I've often heard the term de-encrypt. Decrypt is the correct term. I find that actually very useful when people use de-encrypt, because then I know they probably don't know what they're talking about, but they have some vague idea of how this stuff works. But they're usually not that technical. About the cryptography anyway. They could be really good about other things, like even application security. A hash algorithm is distinctly different from a cipher algorithm. It's a cryptographically secure hash algorithm broadly is like hash algorithms that will be found elsewhere in software engineering. Take a variable length input is pretty common, and then producing a fixed length output. The cryptographic part is, and there's several aspects to it, but basically there's no inverse. You can't go the other direction. And that's cryptographically enforced. The mathematics make it hopefully impossible to do so. Maybe it could be brute forced in some way, but ideally it is infeasible to even brute force it. And I'm also going to talk about defense in depth and how defense in depth relates to cryptography and how that fits in with application security. I often like to use the metaphors that come from the physical security world. Physical security is a lot older than information security in some ways. You could even think of it as being many millennia old. And some of the terminology is very similar as well. For example, there are keys for locks versus cryptographic keys. So in defense in depth and physical security, here's a contrived example. You've got a safe, protects your stuff, and you put that in a building, and hopefully that building has some security. It's got locks on the doors. You've got a fence around the building, possibly. I mean, I'm actually kind of describing a lot of data centers here. There might be, except for the moat, that's not very common these days, but I use that even though it's fairly archaic because the visualization that it provides for people. It's another barrier. And then you might fill that moat with water. Dry moats can be effective too, but fill it with water, that might make it more effective. Maybe not. That's why this can be a useful metaphor. Sometimes defense in depth doesn't actually help. A really deep moat, fill it with water, and now it's effectively not deep anymore. But you could do something else. You could protect that water, maybe fill it with alligators too. Not that I'm advocating alligators as an aspect of application security. And then there are different places that cryptography can be applied, not just as part of defense in depth or defense in depth with cryptography itself, but also cryptography as it applies to the OSI protocol stack. Also a flawed model since we don't really use the OSI protocol itself, but it's a useful model to explain how things fit together. And cryptography could be used at any one of these layers. All of it simultaneously even. That's uncommon. I haven't actually seen a system where it does absolutely everything, cryptography at every layer. But it's useful to point out where it is, a security control, like cryptography, because the further away the security control is from the data, usually the less effective it is. But more transparent it becomes to, say, application developers, which people like in general, especially application developers, because they don't have to worry about it. And if it's transparent for you, it's also transparent for the attackers. So it works both ways. A really important part of this that I want to point out is there are actually two more layers in the OSI protocol stack. I've got the t-shirt too, it's a nice shirt. So to get now into the OWASP Top 10. Change is good. A lot of changes have happened. Your change is better. I originally did this presentation in 2008 for the Twin Cities local OWASP chapter. And I saw that in 2004, there was only one crypto item in the top 10. 2007, there were 3. That was a 300% growth. So I predicted maybe in 2010, maybe there'll be, and you can't quite see it, maybe there'll be 9 items in the top 10 that are all crypto related. Fortunately, that did not actually happen. Sort of. Here's the current top 10 from 2010. Only one of them actually is crypto. I'll explain why I said that there are 2 more too, and there still are, that I think are have strong aspects of crypto. Crypto is generally useless for most of them, except one of the things I like about working in cryptography is there are so many places it can be used. Sometimes they shouldn't be used, but there are so many places where it can fit in where it can be an effective control. And sometimes it's a very small part of the system, but it's really important to be done correctly, and it's easy to do incorrectly. So A3 authentication, their authentication as it's implemented today has strong cryptographic aspects to it, either in the form of, or crypto, there's cryptography, but there are also the cryptological aspects of it. Things like choosing random session IDs. That is an aspect of cryptography. If you want to have a secure session ID, it should be random, it should be large enough. That's now getting into things like information theory, entropy, what's that random number generator, and so on. Then of course there's crypto, and crypto is crypto. And then under transport layer security, of course, that's also cryptography. Although, and this is another parallel to physical security that I occasionally bring up as an analogy, it's quite possible to have a totally secure system that uses no cryptography whatsoever. You just have to have physically trusted channels everywhere. So no cryptography, even in the form of, say, no authentication in the conventional sense, no passwords. You'd have terminals that have locks on them, and you can physically lock the terminal. Of course, there are lots of ways of bypassing that. So the cable that comes out of the back of the terminal, whether that's an old-style green screen type system, or maybe it's actually an Ethernet cable. The Ethernet cable's put in a pressurized pipe, pressurized with gas with sensors on it, so if someone tries to tap into the cable or even just unplug it, alarms go off. There are lots of ways of doing that. Of course, we almost never do that. There are systems built that way, though, especially before crypto got relatively cheap and widespread. So some of the changes in more detail that happened. I'm not sure if they're quite ordered exactly in priority, but I like to think of it as A7 got promoted to A3 in the 2010 from 2008. A8 got up a level. Maybe it's not really promoted, but it's higher up in the list. Maybe that counts for something. Maybe it had to go someplace. No change in A9. ESAPI 2.0 has substantially improved crypto as well, and ESAPI is now being talked about more. People actually seem to be using it. There's a lot of potential there for growth and change. Good growth and good change. So in detail, one failure, and I phrase these as fails. Using HTTP is a fail often with authentication. If the authentication is based on secrets, it's kind of hard not to use secrets. Passwords are secrets. If it's going out in the clear over the internet, I think that's an automatic fail right there. And this is something that's clearly called out in the cheat sheets on the OWASP website. Just a quick survey. Anyone here has looked at the crypto cheat sheets, like the cryptographic storage cheat sheet? Anyone here read it? Okay, I highly recommend you read them. They're both the crypto cheat sheet. How about the transport layer security cheat sheet? The authentication cheat sheet? Okay, read them. They're good. I do have some complaints about aspects of it, though. But generally, they're good. They're good references. But they are cheat sheets. They're short, makes them easy to read, but they do have to gloss over some details. And the cheat sheet, the authentication cheat sheet, calls these out as issues. One of the ways to fail with passwords and password hashes, I really want to call this one out in particular, password encryption and password authentication. I call these out as fails because passwords are broken in so many ways. So unless you've got an application you know is low security, you're going to fail if you're using passwording, and if there's a threat against your system. Of course, if it has high security, the implication is there's actually sort of threat. You've done some threat modeling. You've got some concerns. Maybe it's a bet the business, bet the company kind of operation to trust the passwords. So if you're using password authentication, the general trend is you're going to fail eventually. Your users will use passwords that are too short. They'll reuse passwords. They could use fantastic passwords that they just reused once on some other website. There's no way you're going to be able to stop them from actually doing that unless you do something like generate their passwords for them and don't let them set their own passwords. Who here thinks that's a great idea? Okay. Under adverse circumstances, it could be a great idea, but it's a really bad way to solve the problem. One way to set a user for your set for your users their passwords is to not use password authentication. Do something else. Two-factor authentication, certificate authentication. But usually we're stuck with passwords anyway. It's really hard to migrate to these other things, even though the technology has been around for a while, because it still manages to be immature. Such as the keynote today about PKI root CA problems and some of the solutions. Certificate authentication works really great if you put total trust in the root CAs and they are in fact trustworthy. And also there are all the operational things that they can actually make them work correctly. It can be done in small scale. I've seen it run very well at the small scale. The global scale, I haven't seen it work correctly yet. Password encryption is another fail. I call this out in particular because there's often some confusion between encryption and hashing, ciphers and hash algorithms. Sometimes people, when they say password encryption, they just mean, well, we're taking those clear text passwords as they come in, we put them into a password database, a user authentication database, credential database, whatever it's called, however it's actually done. And then they encrypt it, they've got a cryptographic key, and all of these things are treated just like ordinary, otherwise data, but it's encrypted because of the high sensitivity to it. And then when they do password authentication, password is sent to the server. They decrypt the password that was already on the server, compare them, typical, just a string match. But that means that it has to be decrypted. And that means that it has to be encrypted with something else. That's the cryptographic key. So if you're worried about someone stealing your passwords, so you encrypt them, but you're encrypting them with a key that you also have to keep secret, how do you keep that secret? If you could keep that key secret, why don't you just put your passwords there? Now, there might be a reason to do it that way because you've got a really secure place to put that one secret and it's really small. And you can use encryption sort of like a risk compression function. So instead of taking the thousands of passwords, millions of passwords the site might have and having to keep all of them very secure, if you had a really secure place for one password, that one password could actually be a cryptographic key that you use to encrypt all the others. Except very few sites ever actually do anything like that. They just think, well, okay, we've encrypted it now, therefore it's protected, so we're going to have the key in the system, and they don't think about how they're going to protect that. It usually gets hard-coded into something, or they do something really weird that they think is secure, and because it's weird, it's strange, no one knows about it, they've violated Kirchhoff's principle, and then they get broken into. And their passwords get compromised anyway. Another way to fail is, okay, if they're not doing password encryption, you can do password hashing. Okay, that's an improvement. Then there's no key, because password hashes don't have keys. You just take the variable length input and hash it, and you get the fixed length output, and then that's how you do the password authentication, by comparing the hashes, not actually the clear text. Store only the hashes. The problem is that if you use a fast, efficient hash, that's a fail. It's a fail because if it's fast for you, it makes your servers run a little bit faster because now your authentication process can go pretty quick. It's not loading your servers. It means that when your password hashes get stolen, because after all, that's why you're hashing them, right? Same reason why you're encrypting them, because you're worried they could get stolen. You're doing the defense in depth. Then it's fast for the attacker too, because they can hash passwords too. If you're using the public algorithms, you're following Kirchhoff's assumption, they've got your hash algorithm. They know what it is. They know all the details of it. And you can't stop them from knowing it, because if they manage to steal your password hashes, they probably stole the software that you use to hash your passwords at the same time. They don't even have to understand their algorithm. They just have to use your software. They can steal your data. They can steal your data that happens to be your code, too. Unless you've got some mechanism that protects your code. And if you could protect your code, why don't you just put your passwords there? Again, you end up having to protect something. So you could use a slow, inefficient hash. Now that's slow and efficient for you, but it's much worse for the attackers. And this is well explained in the, I think it's actually under A7, not under A3, but I'm not sure, but it gets into more detail. But I repeat it, just repeating what's in the cheat sheet because it's so important. I've seen this fail so many times. Use a slow hash. Use a hash that's specifically designed for password hashing. Technically, it's a hash that's in a construct that adds in additional things. A really simple way of doing it is you just run the hash multiple times. And because of the nature of the cryptographic security nature of cryptographic hashes, there's no way around it. If you set it to run 10 times, it's going to be 10 times slower, and there's no way to bypass it. So it's 10 times slower for your attacker too, which isn't actually much of an improvement, but it helps. It means if they can crack your passwords in one day before, now it's 10 days. What's much better is to set it to, say, 1,000 or 10,000, and then it gets to the point where they're probably going to give up at some point, and they're going to try attacking someone else who used no password hashes at all or something. It is actually possible to keep cranking it up to the point where it's actually infeasible to crack passwords if the passwords are good enough. Or, but that's assuming that they'll get your hashes and they'll just run the hash algorithm a whole bunch of times on your password hashes. What they could do instead is before they ever get your password hashes, they could, because they're going to know what your hash algorithm is, or they're going to find out eventually anyway, they could pre-calculate password hashes, taking a long list of passwords that they think users might use. There are plenty of such popular passwords out there. Or just do the literal brute force attack, not the dictionary attack, but all the possible character combinations, all those strings of a particular length, and pre-hash all of them, every single one. You could take a million English words, for example, and a few variants of those. Maybe it gets up to 1 billion or so variants. And then you run all of them through the hash algorithm, how many ever times it needs to go, however many iterations. And now you've got this big database of pre-calculated hashes. Now when they steal a hash, they don't run the hash algorithm. They take the hash and they look it up in this big table, and in the table is the hash value and the original password. They just cracked it almost instantly. You can just do a simple binary search to do that. There's an optimization to that called a rainbow table, which keeps the pre-calculated hash table from growing very large. Basically, it's a time-space trade-off. So the space goes down. You can think of it as a data compression technique, not like the conventional LZW type Welch type algorithms, but it's effectively data compression. And then they have to do a bit more computation. They actually have to do some hashes. But instead of doing 10,000 hashes up front or 100,000, they have to do far fewer, and they only have to do it for the password hash that matches the closest. And there are reasons why that matching can actually be done due to the nature of the way rainbow tables are calculated. So you can totally defeat that, or at least make the tables bigger by using a salt. If that salt value doesn't have to be a secret. It doesn't matter if they get that salt value. The idea is that they don't know what the salt value is until your password hashes are compromised. Then when your password hashes are compromised, they have the hash, but they couldn't pre-calculate it because they didn't know what it was. Now they could do pre-calculations, but it's actually better at that point for them to simply attack your hashes individually, not bother doing the pre-hashing. So if they don't know what your salt is, you force them to do the calculations after they get the hashes instead of pre-calculating. That salt needs to be fairly large, because if it's too small, they can still pre-calculate it. It's just time, space, storage issues, and storage keeps getting cheaper. Oh, was there a question? Okay. If you do have any questions, please use the microphone in the center of the room. That way it gets recorded and everyone in the room can hear the question. So, but the salt has to be, well, one, there has to be a salt. It has to change. If it's static, that's a problem, because once they get it, if your site's big enough, if your site is actually worth anything, they're going to be justified in taking that static salt and simply using that one static salt across all of them. Maybe they will pre-calculate, especially if they can do an ongoing compromise and keep getting fresh hashes from you. If it's too small, they can still pre-calculate. It's just a bit larger. Or if they can predict the salt ahead of time. If this is a salt that's used, say, in a web framework, and maybe the salt increments like every day, or every time the system reboots, it bumps it up, or it increments every second. That's still predictable. And there's some information theory reasons I'll get into later as to why if a salt incremented every second, not every time a password is hashed, that would be even worse, but if it were every second, that's still not good enough. So it has to have a salt, it has to be dynamic, it has to be large. 64 bits is a good choice. And it should be a random value, not just merely a counter. And it should really be completely random, but if the randomness isn't perfect, it's still a vast improvement, but it depends on exactly how non-random it is. Basically, the non-randomness reduces the effective size of the salt. If you choose a 64-bit salt, but only has 32 bits of randomness, then you really have a 32-bit salt that just takes up extra space. Then there's, this is not in the cheat sheet, actually the opposite of it is there. I think password quality is a fail, password quality checks. The way they're typically done. The Center for Password Sanity, the link is there at the bottom, talks about these issues with password quality. And I've got a slide that gets into that a bit more detail. The issue I find with password quality, I do put that in quotes, is that it tends to reduce the effective security of the system and decrease usability in the belief that if you make the password look complicated enough, it is complicated, it does have strength to it. It has information entropy is the technical term. So you force people to make them think they know what information entropy is, and they don't even know what the word is. And if it looks secure, then it must be secure. Reality is that it isn't, and it's still hard to remember. A passphrase, if you prevent a passphrase, I consider that a fail. A passphrase is simply a long password. That's it. In terms of how you handle it internally in the system, it's just a longer string. But you have to allow for that. So many systems cap passwords at a particular length. 8 is really popular. I think 8 is way too short just from a cryptographic standpoint. By the way, an 8-character string that could be a binary string, it has only 64 bits of entropy in it. That's not considered a weak. That's considered a strong cryptographic. Sorry, that is considered a weak cryptographic key. It is not strong. For it to be a strong key, would have to be 112 bits. 100 bits could be acceptable too. That's quite a bit longer. There's no way to get more strength out of 8 characters as long as they're 8-bit characters. And Unicode doesn't really help that much either. Just a tiny bit, and usually it's UTF-8 anyway. So it's still 8 bytes. So by using passphrases, you can get a lot more strength. Users can choose as much security as they want, which is another way of doing this. If someone wants to use a bad password on your website, well, maybe that's okay with them. You might be able to guide them as to what would be good, but you could also let them use passphrases, and you could have 2 password quality checks. You could use the regular old ones if someone really wants to use a short password. But you could also tell them outright. The thing I hate is when the password quality thing, the meter, the rules aren't published, so people have to keep on trying a password, different passwords and variants until they finally get a password that the system accepts. I mean, what are you trying to prove that they're a human being, that they can come up with trying to figure out by just guessing and their intelligence what your password policy is? And even if it's printed, that doesn't mean it's necessarily accurate, because the documentation always matches the source code, right? Yeah. That's documentation, but it's for your users. Instead, you can still do that if you want that backwards compatibility, or you could just tell your users, use a 20-character password, or whatever you think fits your security. 20 is a good value. It gets you about 128 bits if they were actually random characters, and it's a lot better security even if they're not random. There are actually ways of estimating the actual strength of a 20-character passphrase that someone would come up with. It's actually not that great, but it's still better than an 8-character passphrase that even if you force them to do the random stuff. And then there's also the problem of non-random number generators, which causes problems with session IDs, for example. Earlier when I said if you've got a session ID and you're using, say, 64-bit session ID or 128-bit session ID, but if what's actually creating that random session ID, assuming it's random, probably should be, if it's only got 32 bits of entropy in your random number generator, it's a 32-bit session ID. There's more detail in the cheat sheet, so I do highly recommend that, but I do have a complaint about the password quality part. It doesn't talk about passphrases either. This slide, this is from the XKCD webcomic. Who here reads XKCD? Oh, great. Okay, there was a bit of controversy about this particular comic. I basically completely agree with that. I've done the math. Actually, I've done this multiple times before I even saw this one. This is just a really great example of the issue. Who's seen this one before? Okay. Any complaints, any questions about why I think this is totally correct? I'd be glad to answer them and elaborate. Otherwise, you can just read the comic. Okay. I've been doing this, basically this idea, since about '98. I used a slightly different system. It's actually one that does use a random number generator. It uses dice. You throw dice. You take the values of the dice values you get, look them up in a table, and that tells you what word to use. And depending how many words you get more security. Each word has over 12 bits of entropy in it. 12 bits isn't very good for just one word, but you can add them together. So 2 words will be over 24 bits. It's just short of 13 bits of entropy. So a 4-word phrase, oh, this is called diceware, by the way, and ends up being fairly secure. Not that great, but a lot better than the troubadour thing there. And the math is basically the same. The one difference is that this word list, that these random words are, I think it's from a 2,000 word list, whereas diceware uses 7,776. That's because that's what you get in base 6 when you throw 6-sided dice and 5 digits. So some more ways. This is an allusion to where there's the overlap between the different items in the top 10. Default keys. That was actually a problem in a SAPI crypto. There were example keys. They weren't intended to be hard-coded keys that people weren't supposed to use. It wasn't intended to be, like this backdoor or something. It was just, here's an example, here's how you can do it. And people didn't change it in some cases. So it's a default. That actually is from A6 though, but it has severe cryptographic implications, just like it does for a lot of other things. But it's really bad for the crypto. It makes your crypto completely fail. Another example is algorithm choice. And two that I have here are MD5, which is a hash algorithm. For integrity purposes, it ends up having about 21 bits of security, easily brute forceable, and has been for some years. Fortunately, the big root CAs are no longer using MD5, but some of them were still using it up until a few years ago, until someone published the next attack against MD5, which finally brought the security down to about 21 bits, and at that point they decided they'd stop issuing them. I won't comment further on that. Moxie Marlin Spike does quite a bit of that already, and he does a good job at it. And then there's SHA-1, which is the current popular hash algorithm for the root PKI and other applications. It only has 51 bits of security. Difficult to attack, but well, with cloud computing getting cheaper and cheaper and cheaper, there are examples of cracking MD5 and other things doing this very cheaply. SHA-1, it's just a matter of time before someone publishes an SHA-1 collision. And then automates at the point where they can start forging certificates. I thought it might even happen this year. Hasn't happened so far. I'm glad for that. Another one of my failed predictions, and I like it when I predict catastrophes and they don't happen. That's great. Sometimes I'm a pessimist. So some other ways that they can fail, more algorithms. 2 TDES. This is where the details become really important. 2 TDES is 2-key triple data encryption standard. So it's a data encryption standard applied 3 times with only 2 keys. It's done 3 times, so you could use 3 keys, but for some reason there's actually a standard for doing it with only 2 keys. Because of some quirks in the way DES works, that ends up not having 112 bits of security, because DES keys are 56 bits long, so 2 of them should be 112 bits of security, which is actually not bad. It's marginal for the next few decades, and the reason why I'm concerned about security up to the next few decades. My pre-conference webcast last week got into that. You can consult that for why I'm concerned about decades-long security. But because of quirks, it ends up being only 80 bits. And NIST deprecated all of the 80-bit security they had previously approved as of last year, which they had published in their standards back in 2005, saying that they would be deprecating them, actually disallowing them at the end of 2010. So many vendors didn't read the stuff they published in 2005 and republished multiple times since then. So they have now deprecated them, which means you can use them as long as they're deprecated, as long as you're taking on some risk, and they will go from deprecated to disallowed unless they change it again because they get pressured in 2013. Microsoft, for example, has said that they're going to be supporting 2-key triple DES and MD5, SHA-1 actually I'm not sure about MD5, but SHA-1 until 2013 because of their own migration and support issues they have. And so the two end up matching up. Another way of saying deprecated is it's okay to use this as long as you're stupid. Really, that's kind of their intent. They did not want to have even deprecated at all. There's allowed, and then there's preferred and better, but not deprecated. So RSA 1024, this is another confusing part about crypto, in this case public key cryptography. RSA 1024 has a 1024-bit key. It does not have 1024-bit security. It never did. This is a common misunderstanding that RSA 1024, that's 1024-bit keys. That's pretty strong, right? 2-key triple DES, that's 112 bits. Okay, why are they different? Well, they're often paired together. Turns out they actually have about the same security. That's because of the nature of the way RSA works. RSA uses large prime numbers that then are multiplied together, and there end up being a lot of optimizations to factor that composite number made up out of the prime numbers. And those optimizations mean that it has about 80 bits of security. I should have asked this earlier. I've been using the term bits of security. Who's comfortable with things like bits of security and entropy and information entropy? Okay, I'm going to explain that just a little bit. When I say something has n bits of security, I'm referring to a very broad concept that includes computational complexity, which includes things like number of cycles that it would take to execute the attack, the amount of storage that's needed for the attack. It encompasses all of these because they end up being often interchangeable, time-space trade-offs, for example. Not always, but it ends up being roughly usable. So the amount of bits of security of the system ends up being based on things like the input entropy. The entropy is the randomness that the system has, the parts that can't be guessed, the secret parts, the parts that by Kirchhoff's principle are the only things that we can actually keep secure. And we measured in bits. We could measure it in any other number. We could say, well, it's like a 1 in a 10 million chance, because it can be expressed as a probability as well. But these things are binary-based systems, and expressing them in bits ends up being extremely convenient. It's also much more convenient to express them in bits than bytes. Instead of saying 80 bits of security, I could say 10 bytes of security. But there are a variety of reasons why they're expressed in bits. Partly for consistency, partly because the term byte is actually ambiguous. It's not always 8 bits, almost always. In the past 10, 15 years it is, but there are exceptions. And cryptography goes back far enough, bit is used. There are also other measurements of information entropy, like the band, for example, which actually does use base 10, but is rarely used in modern work. So if something has no bits of security, there's no security at all. If it has 1 bit of security, it means that the chance of breaking into the system is, one way of looking at it is in a single attempt to break into the system, there's a 50% chance that the correct bit will be guessed. And if there are 2 bits, then it's a 1 in 4 chance, because there are 4 possible values of 2 bits, so it's a 25% chance. So I have a 25% chance on the first try. However, I can keep on making tries, and if a try only takes, say, a year, then I can break that 1-bit system in 2 years, or 1 try per bit. If I'm lucky, I'll do it on the first try, and there's a 50% chance I'll break it in the first try. Pretty good odds for the attacker. By adding on more bits, you reduce the chance they'll get it on the first try. And there are more bits, more states to go through, more possible values. So in order to be guaranteed to break the system, you have to go through all possible values. So if you make that long enough, they will not have enough time to go through all possible values. What you really have to do is assume that on average, that it'll average out to the average. And they will end up being able, they only have to guess half or make half the number of possible total attempts to actually break in. Whether they actually will, it's totally random. At least it should be if you're using a random number generator for setting these various values. So if you have 80 bits of security, to go through half of all the possible 80-bit values is 79 bits. So if you have a system, an attack system, that can go through all 80 bits of state, and iterate through all the possible values that the victim system could have, you only have to go through about half of them on average. Now, this is sort of related to word size on computers, 32-bit, 64-bit, the older 16-bit systems. So these bit values partly correspond to that, but a 64-bit system has no problem at all calculating 128-bit values. So same thing for 32-bit systems. It is slower. Oh, only 1 minute? Oh, I've got quite a bit more to go through. Sorry about that. So confusing encryption and authentication is another issue. The crypto cheat sheet goes into quite a bit of detail on that. It needs more guidance, however, because it gives you a whole bunch of things you could do, but necessarily wouldn't want to. Another crypto fail is inventing your own crypto protocol. Another is using someone else's crypto protocol and assuming that just because it's CIPS 140 validated that it's perfect. They're not. They have been known to fail in very public ways. There's a link right there that tells you where to go. Non-random number generators, which I've already talked about. And this is more about random numbers. I'm going to have to skip over some of this. Anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. A classic quote from von Neumann. These are things I've actually seen, 30 bits for the time of day. As the time of day value, I've mentioned before. No weak seed, well, no seed at all possible keys are compromised. The OpenSSL Debian vulnerability. Persistent seed pools, that's another area where just the entropy is not enough in the system. Unfortunately, random number generators are not well standardized. There isn't even a random number generator in NSA Suite B, which is an up-and-coming suite of cipher algorithms which are otherwise well chosen. There's just no RNG there. This is another way you can fail. That was a random value, but one, it's now static. It's not per instance. And it's probably way too small, because if it's only 4, the chance of that being a random 128-bit value is actually very, very low. It's almost the same chance as just randomly guessing any 128-bit value, but not quite, because it's not 0. And then there are ways to fail with transport, and this is another overlap. HTTP is a transport fail for confidentiality. And because HTTP doesn't have an option for integrity built into it, it's an integrity fail as well. Although you can add your own layers on top of that to give you the confidentiality and integrity you might be looking for. And I apologize for running over. SSL can be a fail as well, because SSL is the older protocol. TLS is the new protocol. Although technically it's just a name change, so there's actually an SSL version number that corresponds to TLS 1.1. TLS 1.1 is a fail as well because it's got vulnerabilities in it. Fortunately, these are less commonly used, although there's actually at an information security conference in a couple hours, there's going to be a presentation on an attack that might actually work against TLS 1.1. It's actually a known vulnerability, just no one's published exactly how to do it before with a tool. We'll have to see what comes out of that. But there might be nothing there, there might be. And there's the transport layer protection cheat sheet. I highly recommend it. So, and of course, if you're using password authentication and you're doing the transport fail, well, then you're failing again. It's another one of those overlaps. If you're doing exportable cipher suites, that in the past, the United States government restricted which ciphers you could use outside the US, and rather than having 2 different sets of cipher suites, some companies just did the exportable, or it was just difficult enough to get the non-exportable that that's what people defaulted to anyway. That's a fail. Exportable cipher suites have only 40 bits of security. And when there used to be export restrictions. Now the restrictions are more or less gone. Not quite though. Talk to your lawyer. There are weaker cipher suites out there as well, not necessarily exportable, but not quite as strong, such as technically DES was not exportable for a while, so it's weaker, very weak, but wasn't actually exportable, so that's why I included both. So why is this all so difficult? Well, cryptography could be estimated as being about 3,000 years old. Maybe even as old as language itself, or slightly younger, or maybe slightly older. If cryptography predates what we think of as clear text communication. Maybe it does. Okay, I have to wrap up now. This is just about my last slide. Just about all the crypto has been broken prior to 1977. What we've got today is just not broken yet, but fortunately it hasn't been broken yet. And maybe it won't be if we're lucky. So, questions? Feel free to ask me questions by sending to my email address, anthony.j.stieber@gmail.com. Thank you.